So to begin with, I'll try to give an overview of what machine learning is, and then we can go over a few applications and then specific models that we use for machine learning. And I'll end with a few pointers on how you can go out and explore these types of methods with different data sets. So in general, machine learning is a category of algorithms that use data to learn something by themselves, where a human doesn't have to go in and make specific rules or like edit things. And the algorithm itself becomes better and better, typically with more and more data. And oftentimes these algorithms are trying to replicate some type of human behavior, whether that be translating text from one language to another or identifying what an object is or where that object is. And over the past few years, two big, huge things have happened. One is we're able to collect massive amounts of data, and we're able to have a lot of really high quality labels on that data. And then the second thing is we've made huge strides in computational power, which means we can take all of that data, process it using these machine learning algorithms very efficiently. And the result is that these types of algorithms, even though they've been around for like 100 years, um, in the last few years have become extremely powerful and extremely accurate. And not only are they oftentimes just replicating human behavior, they are able to exceed it. Oftentimes, like doing things that no one single human would be capable of doing. And that's why they make a really powerful tool for any type of scientific and research exploration, because you can label really complex phenomena or understand data in a way that maybe in the past would have taken 10,000 humans many, many years to do, and we can do in a matter of seconds. But in general, typically you need some kind of model and you need a data set. And together you can create some type of algorithm that recognizes things. I'll go over a few different applications of machine learning that you might be exposed to in your own life. So one of them is maps, whether or not you're on your phone or even in your cars. One of the things that new mapping systems take into account is not only your location, but also factoring in traffic around you, road closures, multiple types of events, and they have to optimize many different vehicles moving at the same time so that they don't create traffic, and they efficiently spread it around. And doing that by hand would not work because people are mapping themselves all over the world all the time. And we need an algorithm to automate that process and to run constantly. And it needs to be able to feed in data like at every single second. This second example, I linked a story actually that describes it. And it's a really interesting case where people use machine learning to identify different types of pastries. And the reason was that a particular bakery had so many different varieties of pastries that it became cumbersome to have like a barcode next to each pastry to be able to exactly understand the price of each one. And so instead, they created an algorithm that could look at a picture of each of these pastries during checkout and tell you exactly what the correct price was. And someone saw that algorithm and they actually thought, okay, maybe we can use this to identify different cancer cells. And they were actually very successful in using the same approach to identify cancer and help human health. Another really common use of machine learning is spam detection. So one way you could try to filter out spam in your email is come up with big lists. So whenever an email is sent from a specific type of email address, we say it's spam, or maybe if it has a few different keywords, it could be spam. But at some point, having humans write down all these rules would become untenable because anytime someone comes up with a new type of spam email, we're going to have a human need to look at it and understand what's going on. And so instead, we can have an algorithm automatically look at that content and understand what types of sentence structures, maybe the time it was sent, um, the type of graphics and links that they have, and automatically understand that a particular email has a high probability of being spam. Another really interesting health application is using computer vision, which is a specific type of machine learning for understanding images to diagnose diabetic retinopathy. And the way they did this is they took many images of the eye and then had multiple doctors label them to understand if someone had that condition. And then you can feed all of that data into an algorithm. And then that algorithm can automatically take a new image of the eye and label it. And what's nice about this is that if you have all of that information embedded in an algorithm, it can be much more consistent. And then you don't have to rely on any human to make that diagnosis. You can run it on millions or billions of images in a matter of minutes, as opposed to having humans go through and look at each one. And maybe someone's tired, or they're not able to see the screen correctly at that particular point in time. And none of those issues or biases come into play. Another really important development is for security purposes. So oftentimes the latest types of phones will use face unlock. And what they're doing is they are looking at your face, feeding it into a machine learning algorithm on your phone, and then identifying whether you are the owner of the phone or you're someone else. And there's a lot of complexity here because um, in particular, they want to make sure that these algorithms don't work if you just show a picture of your face. They have to be able to look at depth information and some kind of movement to understand, is this a real human in front of the camera, or is it some kind of image spoofing it? And to embed all of the different scenarios and complexities of lighting conditions and orientation and pose, we need machine learning algorithms to have that ability to look at tons of diverse scenarios and make a very accurate prediction on whether you are actually in front of your phone. Another situation where machine learning is actively used is on things like Netflix or other streaming services where they recommend shows or music to you. And typically it's a combination of looking at what people in aggregate like all over the country and the world, what types of shows, different subcategories of people would be interested in, and then also looking at your own feedback in those systems on what things you thought were interesting, what shows you stopped watching midway. And that's all factored into an algorithm that personalizes recommendations for yourself. And then another really ubiquitous part of people's lives these days is having these digital assistants, whether that be like Amazon, Google, or Apple assistants on your devices, where you can just say a hot word and they will talk to you and answer questions. And the idea is that they're always listening for that hot word. And the algorithm running on these devices is very robust to different voices. Sometimes they can actually even recognize a specific identity and only provide personal information to that person and not answer with specific times on like a meeting in your own calendar to someone else. So I said before that these algorithms need data to be able to learn these types of complex, like human or biological or physical phenomena. And within machine learning, there's a bunch of different subcategories. In most traditional scenarios, so for example, like we work with supervised setups. And that means you have a bunch of data and you can say, like, here's an image of an eye, here are people who have a disease, and here are people who don't. And you have that label beforehand and you feed that into your algorithm. And then your algorithm can tell you for a novel image, does it showcase the signs of someone with a disease or not? Another really important mode of using machine learning is unsupervised learning. And we talked about that a bit in an earlier lecture when we are trying to come up with categories that we don't know the labels beforehand. And this means that our machine learning algorithms can automatically separate different subcategories. So for example, if we feed in a data set with the numbers 0 through 9, oftentimes machine learning algorithms can automatically cluster them into different groupings. And then we can look at those different groupings and process them in some other step. Another one that I'll talk about in the future is we can have our algorithm generate data. And oftentimes this type of scenario work, a really good example of that is within games. So for example, in the game chess, we can have our algorithm play a virtual chess game, and it can almost make an infinite amount of data. It can keep trying different moves and see how the board changes, and then use that data to feed it back into itself to come up with new moves and look at multiple different types of scenarios. And so in this situation, we kind of create this virtual world where a machine can interact with it, and then every time it interacts, it can make some kind of conclusion and learn from that. Another really important aspect that you'll see a lot in machine learning is splitting your data into training and test sets. So on the top here is a typical split of training and test. So typically the majority, like let's say 80% of your data will use to training. And training is the data that feeds into your algorithm so it can learn all the parameters of the algorithm. And in the bottom is kind of a simple example. Let's say we're trying to classify the yellow dots or the orange dots versus the blue dots. And so on the left, we have our training data, which is densely sampled. And on the right, we have our test data, which it's a much smaller data set. But the goal here is we actually want them both to be sampled from the same distribution. So if we're going to learn something detailed about our training data, it should hopefully come from a similar space as your test data, because in the end, we want to make sure that it generalizes well to the test data. And this is a common setup that will happen when people are developing machine learning algorithms. But one of the biggest issues, like one of the problems that can come up here is if you only have one test data set, oftentimes you can just keep relearning your machine learning algorithm so that you keep coming up with new versions that do better and better on your test set. And the idea is a test set is some kind of independent sample that tells you if your machine learning algorithm is doing well. But if you look at your test set multiple times and then go back and change your algorithm to try to do better on it, in reality, your test set sort of becomes part of your training because you're feeding it into your decisions when you make changes to your algorithm or you update parameters. And that's a really big problem because in practice, what you want to do is build a machine learning algorithm and then use it for some kind of scientific study or use it in some real world scenario. But if you have fine-tuned it and overfit it to your test set, what that means is the machine learning algorithm is actually memorizing that test set, and it might not generalize well to any new type of data sample that it hasn't seen in the test set. And so one way to get around this issue is actually to come up with 3 different splits. One would be your training data set that we've talked to. In addition to this is a validation set. And so if we go back to that scenario, every time you change your machine learning algorithm, you do something different about it, you want to evaluate, does it work well? And the way we can do that is instead of looking at our test set, we have this separate validation set that we can iterate on and keep trying out. And then when we feel satisfied that we have a good understanding of our problem space and our algorithm is working well, then we can confirm that our results are working on our test set. And in an ideal scenario, if you have a very large amounts of data, you can make sure that your test set is never looked at twice. So for example, anytime you look at your test set, you're not allowed to look at it again, and you have to come up with a new type of test set. And ideally, that's the best way to do that. Um, and oftentimes with machine learning, they will have competitions, which I'll talk a little bit more about at the end of the lecture, where there are websites online that allow you to download different data and give you a problem setup or something that you need to predict. And then competitors all over the world will develop machine learning algorithms to evaluate if they've come up with some new type of architecture that works really well. And when they run these competitions, they're really careful to not allow competitors to look at a test set data. And so what can often happen is if they send out the validation set, people might think that they are doing really well on this validation set over time. But a huge issue with machine learning is you can start to overfit on this validation set. And basically what happens is your machine learning algorithm starts to memorize the validation set. And it can be misleading to think it's doing really well. You'll get really high accuracies, but then at the end of the competition, they take all these algorithms and they evaluate them on the test set. And all those rankings could change. If you've overfitted and your algorithm is memorizing the validation set, it's probably not coming up with a general understanding of like some kind of real world phenomena. And you need to be careful to not like overfit to it. And there's a bunch of approaches to ensure that happens. Like one is a technique called regularization, and that is a method to simplify your model so it doesn't even have the ability to look at the validation set. Other ways you can do that is just not not evaluate too many times on your validation set so that you create like this feedback loop that runs too long and you just do it for a set number of times. And those are ways that you can get around the overfitting problem. Um, and then there are other scenarios where you might just have a data set that is so gigantic where this is never a problem. You might have like 10 billion training images and your algorithm has no capability of memorizing like all those types of scenarios and images that it ends up not being a problem. Next, I'll go into a few different common machine learning tools that you'll hear about, oftentimes in publications and the literature. And one thing about machine learning is like every year or two, there's some kind of new method that comes into the literature that everyone gets really excited about and tries to apply to everything. So one of the standard methods that people use in industry and academia is logistic regression. And you can think of it as taking input many different variables, and then the output of this is sort of like a probability between like two like binary classes. So for example, in this setup on the left, we're looking at the hours of studying versus the probability of passing an exam. And so you can see like basically this is some kind of complex like nonlinear relationship showing like the more hours you study, the like higher your probability of passing the exam. And they use these types of techniques for calculating credit scores or even your risk for a lot of diseases. And what's nice about this is it's very scalable. In some ways, it's very easy to understand the inputs, how they're used in your outputs. There's a lot of interpretability in these types of techniques, which makes it nice because you can understand, given the types of input data and features, depending on like maybe your age or your like risk factors for coronary heart disease, you can understand how important are each of those when this algorithm is making a decision. Another really common algorithm that used to be used in many scenarios is support vector machines. And you can think of this on the left as a support vector machine is creating this type of boundary between two different classes. So on the left is like a really simple 2D example where we come up with a boundary between the blue dots and the red dots. And what's important about support vector machines is it focuses on generating this boundary by looking at this neighborhood of points around the boundary. So in this example, the circled points are actually the most important points when it tries to create this boundary. And it doesn't factor in points like very far away from the boundary, which can actually be really nice because it's not as sensitive to outliers. And then another really important attribute about support vector machines is that it can create very complex boundaries between different classes by projecting your data into like a very high dimensional space. And there's like a special trick used in machine learning to make that whole process very efficient. So in the past, people would use these support vector machines because they were both very efficient, and it was kind of intuitive to understand what it was doing with the data to make different types of decision boundaries. And you can see here, these kernels are the way that we're able to project our data into a high dimensional space. And so if you use like a linear kernel, you'll get like very like linear boundaries between classes. Um, but if you use like a more complicated types of phenomena and classify more complicated things. Next, I'll go through like probably the biggest change in machine learning called neural networks. One thing I know is, let's see, 5 years ago, I was really involved in neuroimaging research. And at the time, neural networks was just becoming part of like the methods that people used. And now, like 5 years later, all of the papers use neural networks. It's like anytime you're doing research, you have to use some kind of neural network, and it's sort of like swept the whole field. And in general, the most powerful techniques in different challenges of whether it be like translating different languages or identifying different objects in images, the best techniques in the world are all based on neural networks. And this is a rough understanding of what a neural network is. On the top left, you can see a really simple neural network. And the input layer you can think of is just numbers, or you can think of it as pixels in an image. So for example, let's say we had an image of a car, and then we had another image of something that wasn't a car. You can think of stacking all of those pixels, and each of those pixels would represent one circle in the input layer. And what a neural network will do is it will take some kind of linear combination of those like pixel values and then feed that into the second layer. And that's what these arrows mean. So if you look at the first hidden layer, the top circle is a combination of those three different pixel values. And each of those pixel values can have a different weight. So the first one could have a weight of 5, the second one could be 10, the third one could be 20. And then once it goes into like once all of those values are combined, typically there's some type of activation function. So that activation function could be just weighting it as one, basically doing nothing at all. But oftentimes it's some kind of non-linear function applied to it. And so on the bottom here are three very common non-linear functions: a sigmoid, a tanh, and a ReLU. And so what that does is it takes like that linear combination of pixels and it does some crazy operation on that. And then the whole process happens again. We take some linear combination of that, feed it into a nonlinear function, and then at the end, we sum it all together. And there's a ton of different variations and operations you can do. But the idea is you can build up this complex network of operations on your data, in this case, like in this example, like pixels from an image. And in the end, you get out your answer as to whether that image is of a car or not a car. And then there's an algorithm that sets up all of the weights and connections in this network automatically. So you don't have to figure out how to do it. There are techniques where you just feed in a bunch of images and that neural network fills in all the right numbers. So it can actually like take in an image and tell you what the content of it is. And in the past, the sheer computational power needed to do this made people think that neural networks were not useful. But what's changed in the last few years is that now, like on a desktop computer, we can actually train really powerful neural networks efficiently using things like GPUs, which process things really quickly. And then a lot of these like big tech companies will come up with their own specialized hardware to train neural networks and make this really efficient. And what you can do now is you can make these neural networks extremely complex. You can have a billion different operations happening in these neural networks, and they can enable you to do like amazing things. So for example, with some of the neural networks that Google uses, we can create these algorithms where you can point your camera at any type of object and it'll tell you like exactly like the species of dog um, that you see, or like if you point it to a building, it can tell you where exactly in the world you are and what that building is and give you some history on that building. And the whole idea here is that that neural network is able to embed all of that really complex knowledge about the world into itself in a actually a very efficient representation. And you can often run this neural network on your phone and automatically classify different types of trees around you. And it can do something that no human can. It can memorize a billion different categories and names, something that just one human can't. And it's really distilling all of that knowledge together. Another really important subcategory of neural networks is called recurrent neural networks. And what's important about these is that they're designed to explicitly factor in time. And the way they do that is they have this pretty complex setup inside where they're able to come up with some representation of the past and then combine that with the present to make a decision. And one of the common types of recurrent neural networks is called long short-term memory. And that actually made significant improvements in machine translations, meaning it could translate an English sentence to Chinese, French, German, Japanese, all at the same time, using this type of LSTM or recurrent neural network. And this was a huge um, technological breakthrough because at the time when LSTMs were applied to the problem machine translation, they were able to improve the quality of translation by 60%. Um, Another really interesting neural network is called generative adversarial networks. And I'll give you an example for how this works. Basically, you can take some kind of random input and then feed it into your generator and it'll create something. And then you have a real image of that thing you're trying to create and you compare them together. And then the whole neural network can modify that generator algorithm until it starts creating things that look like real life. So here's an example. On the right are two columns. On the left is the generated data, and on the right is the real data. And our goal here is we want to come up with an algorithm or a neural network that can generate money that looks real. And the way we would do it is we first have our generator create some random image that it tries to make look like money. And so on the first row, that's the generator algorithm's representation of a $10 bill. And on the right is the actual $10 bill. And our discriminator looks at those two outputs, the real data and the generated data, and makes a decision to understand like which is the real one. And our goal is to have it so that the discriminator cannot tell the difference between the generated and the real data. And what's nice about neural networks is we have this automated method to provide feedback to the algorithm. So that first iteration, when the discriminator says to the generator, hey, I know you're faking this, you're not real data. At that point, all of that information is fed back into the network in a process that improves how the network works. And so the second iteration, or like let's say the 10th iteration, the algorithm has gotten better. It's not just like some random circle somewhere. It sort of is starting to make a face. But the discriminator can still tell like, hey, there's the real money on the right is still a lot better. But if we just keep training in it for a really long time, at some point, the generator will be able to fool this discriminator algorithm and come up with some representation of money that actually looks real. And so the way this is set up is you sort of have these like two neural networks competing with one another, one generating a lot of data, and then one trying to say like, is this generated data real or fake? And what this allows you to do is these really incredible hallucinated data setups, where on the left you can see all these different faces look like real humans you see outside, but in fact, none of these humans actually exist in real life. These are an algorithm just generating different types of faces based on data it's seen in the past. And what's kind of cool is you can create some kind of general face and then like switch the gender, switch the age, um, change hair color, change a lot of different attributes about people. And because it has some kind of complex representation of what a human looks like, when it generates this data, like all the faces look like real people. On the right is another example where instead of generating faces, it generates objects. And if you at first glance, all of these objects looks real. They just look like someone took a photo of something. Oftentimes, though, if you start looking really closely, you can kind of get insights into what the neural network is doing and like see very strange things about the representation. So, for example, in the second column, uh, the first row, there's a horse, but if you look like really closely, it doesn't really have an eye. But in general, the shape is kind of correct. And so one of the applications of this is you could have a case where data is very scarce and it's really difficult for you to get more data. But at the same time, you want to be able to generate uh, enough data that you can train a really accurate neural network. And one way you could do that is you can use this generative adversarial paradigm where you have this generative neural network generating almost an infinite amount of data, and then you're able to use that data to come up with a better classifier. The next type of learning I'll go over is reinforcement learning. And this is that example I talked about at the beginning, where we can explore a game like chess, and every time we make a move, the algorithm can understand that setup of the board and learn something from it. And this is sort of the setup for how um, it it understands how to incorporate new data into its algorithm and optimization. So, for example, our goal might be to win a chess game. And then at every point, the algorithm has many different moves that are possible. And then each move gets it closer or further away from winning the chess game. And that can be quantified in a certain way. And then we can have this loop where it performs certain actions. It looks at how does that improve the solution of this game, and it can keep trying different scenarios. One really interesting way that this can be useful this type of learning can be useful is trying to come up with the intelligence to move a mechanical hand and pick up different objects. And so on the right, top right here is an example at Google where they have this farm of arms that all day long pick up different objects. And each of these objects will have different weights and different densities and look very different. And so the algorithm is learning throughout time where it picks up different objects and it sees how much pressure it should use, um, how easy it is to move them around and how much like effort it needs to do that. And every time it picks up an object, it can see how did that object react and embed that into the algorithm so that after a while it understands that if an object looks a certain way, it'll probably weigh a certain amount and require a different amount of pressure from the grip to lift it up. And it's a really nice setup because we almost have an unlimited amount of data to feed into the algorithm because the algorithm itself is sort of reacting with the world in an infinite number of ways. Another really interesting application of reinforcement learning is video games. And they've applied it to a lot of the older video games on the Atari system, like Pong and things, where you can have your algorithm control one of the players and then see how um, the environment reacts when the algorithm makes a decision. So on the left is a game where I think it has to like shoot a bunch of spaceships. And so the algorithm over time can understand what moves get it closer to winning the game. And if it's trained long enough, it can perform at a superhuman level because it can do every action immediately in a fraction of a second. And this is a really nice paradigm because it's one way we can get around that issue of not having enough data to learn different algorithms. And then for you, if you want to go out and try these methods, you can. I think the one of the most popular toolkits in the literature is PyTorch. Another really widely used one is TensorFlow, and these are both machine learning tools that have all the latest like implementations for neural networks. If you want to try, oftentimes when people publish a paper with a new neural network technique, they will also provide an implementation in PyTorch or TensorFlow. And then if you want to figure out like what are interesting problems that are available, you can go to Kaggle. And there are a bunch of other sites that are similar to Kaggle as well, where companies or universities will upload a data set and they will open it to the public to compete for different types of neural networks or different types of machine learning algorithms in general to solve a problem, whether that be like classifying different types of trees or classifying or predicting different financial markets. They will open this up to a competition and typically they'll have that competition run for a couple months and the top 3 winners will get some type of prize. And what's kind of nice about these websites is they form a community. So if you participate in these competitions, oftentimes other participants will share code for how that they analyze the data and give you tips on what they tried. And a lot of new algorithms have come out from these sort of competitions that help people try different techniques out in the community. And it also gives you access to data sets that people have curated and that we know work really well, or we know that are really hard problems and we need people to start coming up with more creative approaches to try to solve these types of problems. And yeah, that's all I had today. All of this stuff, like all of these resources are free. So if you want to try them and experiment with them, you can.